when we have an object undergoing harmonic motion, we know something about the forces on that object. And let's go back to our little demo here and think about it. So here we have a spring that is stretched to some length. And here we have a mass attached to that spring. So if we look at a free body diagram of this spring mass system, we know that this mass feels a force down from gravity, and it feels a force up from the spring. And right now, sitting here motionless, those two have to be in equilibrium, right? The forces up and down are balanced, so there is no net force up or down. It is not accelerating, and maybe there's some friction from it rubbing against the board, but we're gonna ignore that. This works out the same whether or not that friction is there, so we can pretend there's no friction for the time being. Now, what happens if we displace our object from its equilibrium position? So let's say I take it and I lift it up a little bit. So what have I done to my system? Well, I've shortened the spring and raised the mass. Now, the force of gravity depends on how big the mass is, and that hasn't changed, right? My force of gravity is still the same size. But my spring, now instead of being this long, it is only this long, which means it is going to be exerting less upward force. So I have a smaller spring force upward if this is above its equilibrium position. So up here, Fs is smaller. If I pull it down from its equilibrium position, so then we have our spring really stretched a lot. Now our free body diagram, I'll try to cram it in here. Our free body diagram still has the same downward force of gravity, the same size. But now the upward spring force is bigger because we have stretched our spring more. And remember, F equals K delta X, where delta X is how far we are from our equilibrium length. So the bigger the spring is, the bigger this force, the bigger this force exerted by the spring gets. So these are our two. So this situation is equilibrium. These two are away from equilibrium, and down here we have our spring force bigger. So the result of that is that when our mass is up, looking at this free body diagram, we end up with a net force down. Here, where our mass is below, our spring force is bigger than gravity, so we end up with a net force up. Okay, so I'm going to erase all this just to make some room. The result of all of that is that if we're at our equilibrium position, the sum of our forces is equal to 0. If we're above our equilibrium position, our net force, so let me rewrite the sum of the forces as the net force, that'll be a little easier. So the net force is equal to 0. Above, our net force is in this downward direction, and below, our net force is up. So what this means is that wherever we are relative to our equilibrium position, at any instant in time, freeze this picture, we have a net force pushing us back towards our equilibrium position, right? If we're above, we have this net force pushing down. If we're below, we have this net force pushing up. And it turns out in this case, the further we are away, the bigger those forces get pushing us back towards this equilibrium. Okay, so the takeaway from all of that is that in this system, as well as many others, as we'll talk about in a second, our net force pushes the system back to equilibrium. This is called a restoring force because the nature of the force, changes, but is always trying to restore our system to its equilibrium position. It's always causing this to accelerate upward when it's below its equilibrium position, and when it's above its equilibrium position, it causes it to accelerate downward. All right, so this is the idea of a restoring force. Restoring forces show up a bunch of places in oscillations, and in this class, all of the oscillating systems that we'll see have a restoring force that is trying to push our system back to equilibrium. So for any mass on a spring, you'll have something similar to this. Anytime you have a mass connected to a spring, you'll have a restoring force where the spring is trying to push the mass back to its equilibrium position, which is the equilibrium length of the spring. Here's another system where we can look at the restoring force. And that is a pendulum. So a pendulum is, at its simplest, like a mass hanging from a string that's allowed to swing back and forth. It doesn't have to be a string, it could be a rod or anything, but it's allowed to pivot at the top, and this mass, swings back and forth like this, So when we have something that looks like this, let's look at just this left half here. So if our mass is to the left, well, first of all, where is the equilibrium position? Well, I think it makes sense that if our mass was hanging straight down, we know that the free body diagram looks like tension up, gravity down, and tension is going to be as big as it needs to be to keep the string from stretching, so these two are going to be equal. So at this vertical position, this is our equilibrium position. Okay, if our mass is pulled off to the right here, so we displace it to the right with this like counterclockwise rotation, now what forces do we have on it? So if we do our free body diagram, we still have gravity straight down. Now we have our tension up and to the left, and you can figure this out yourself, or you can believe me that the net force is going to be this component of gravity that's perpendicular to the string. So this is, we'll call that Fg perpendicular to string. We're not going to do any computation to this. I just want to show you that this is a component of gravity, and this is pointing us back to the left. So this tension is going to cancel out with this component of gravity, and we're going to be left with a net force of gravity pushing us to the left, which is clockwise. Over here, our net force is going to be to the right. So here again, we have a force that is trying to restore us back to this vertical equilibrium position. So our pendulum also has a restoring force, and because of that, also has this oscillating behavior.